Hello everybody and welcome back to another video. In this video I will be covering linear air resistance, specifically how to form a function of velocity in terms of time with a linear drag on an object. So let's start off by defining linear air resistance. So linear air resistance just means that the force of drag is correlated to the velocity of an object. It is not the velocity squared of an object, as that would be quadratic air resistance. So that means that FD is correlated to V squared. Now you might be thinking, well, why do we use both? Well, it actually is because it is a combination of the both of them, technically, but that is not what we'll be doing today, nor will we be using any of this, unless you want to see that in a future video. That video will probably be around 30 minutes long if you want to see that. So that is a very complicated video. However, in this video, we're assuming FD is correlated to V. So what does this mean? That means that the force of drag is equal to a negative constant times V. Now that is because when you drop something, the velocity is going that way and the force of drag is going opposite in the direction of the velocity. So it is a negative constant times V. So let's draw our free body diagram of this. Now in this, we are assuming that it is dropped from an initial velocity of V sub 0 at a time, which is T sub 0, which is just equal to 0 seconds. Now, there are two forces on the subject. There's a force of gravity downwards, which is just equal to the mass times the gravitational acceleration. And then there is a force upwards, which is the force of drag, which is equal to negative C times V. So we will start off by making a net force equation. So this is F net, which is equal to the sum of the forces, is equal to Fg plus negative Cv. So this is just Fg minus Cv. Now we also know that F net is equal to the mass times the acceleration, so that is equal to Fg minus Cv, which we can rewrite as mg minus Cv, since the force of gravity is just m times g. So I'm going to go ahead and divide both sides of this equation by m, which gives us that A is equal to g minus c over m times v. So acceleration is just the time derivative of a velocity. So we can write this as a differential equation right here, which says that dv over dt is equal to g minus c over m times v. So we are going to go ahead and multiply both sides of this equation by dt to get this by itself. And these cancel, and we get dv is equal to g minus c over m times v dt. Now this dt cannot do anything to this v as it is a function of velocity, so we actually have to go ahead and divide both sides of the equation by the g minus c over m times v, and we can just get this equation right here where these two cancel out, so we get 1 over g minus c over m, v is equal to dt. Oh, this is multiplied by dv, by the way. Now we are going to integrate this on both sides. Now we have to integrate it with respect of velocity on this side and with respect of time on this side. So we know that t sub 0 is equal to 0 seconds. So we are going to integrate it from 0 seconds to our time t that we are looking for. And we also know that at time t sub 0, which is 0 seconds, we have a velocity of v sub 0. So we'll put that on the bottom. And we are looking for a velocity v at that given point t. So now the integral of dt is just going to be equal to t evaluated from 0 to t, which is just equal to t. So there are no constants of integration here since we have bounded integrals. So this tells us that the integral from v sub 0 to v of 1 over g minus c over m times v dv is equal to our time. So we are going to do this integral right now. So let's get rid of, or we could leave this work. So we have the integral from z sub 0 to v of 1 over g minus c over m times v dv. And that is equal to our t. So we are going to just do a u sub on this right now. So we have u is equal to g minus c over m times v. And now we will differentiate on both sides with respect to v. So this gives us that du over dv is equal to negative c over m times v to the 0, which is just 1. So now we're going to go ahead and multiply both sides by dv. And we get du is equal to negative c over m dv. Now we are going to multiply both sides by m over c. And that would actually be negative m over c. So negative m over c, canceling out all this. And this gives us that negative m over c du is equal to dv. Now we can go ahead and plug our u in right here and our dv in right there. So we get the integral from a new bound, which I will just call alpha to beta for now, of negative c, or I'll do this later, of 1 over u, and now we have du negative m over c times du, and since these are constants with respect to u, we can just pull them out, and we get negative m over c times the integral from alpha to beta of 1 over u du is equal to our time t. Now we will just integrate this. The integral of 1 over u is just the natural log of the absolute value of u. So we get negative m over c times the ln of the absolute value of u. And if you remember, u is just g minus c over m times v. So the ln of the absolute value of g minus c over m times v evaluated from, now we can go ahead and replace these bounds since we're not in terms of u anymore, v sub 0 to v is equal to our time t. So now we will go ahead and first let's multiply both sides by this c over m and negative. So this cancels all this out and we get negative c over m on this side. So this gives us that the ln of the absolute value of, wait, I'll draw an arrow there, the ln of the absolute value of g minus c over m times v evaluated from v sub 0 to v is equal to negative c over m times t. So now let's go ahead and plug in our v and v sub 0. So this gives us the ln of the absolute value of g minus c over m v, as we plugged in our v, minus the ln of the absolute value of g minus c over m times v sub 0 is equal to negative c over m times t. Now we know that the ln of this minus another thing, that, or I'll write this up here, the ln of the absolute value of a minus the ln of the absolute value of b is equal to the ln of a over b due to natural log rules. So we can go ahead and move this over here and rewrite it as such. So I will erase over here, and we can go ahead and bring this over here, and this gives us the ln of g minus c over m times v divided by g minus c over m times v sub 0 is equal to negative c over m t. Now raise both sides to the e. And since this is the absolute value, we will just add a plus or minus over here, e to the negative c over m times t. But we will just use the plus value because of how we defined our directions. So this is just e to the negative c over m times t is equal to g minus c over m v over g minus c over m v sub 0. Now we are just trying to get v by itself. So let's go ahead and multiply by this denominator, c over m v sub 0, g minus that, and these cancel, and we get g minus c over m times v sub 0. This gives us g minus c over m times v is equal to e to the negative c over m times t times g minus c over m times v sub 0. Now we are going to add or subtract g from both sides. And this gives us that negative c over m times v is equal to this right here. So let's go ahead and multiply by negative m over c to cancel this out. So this is all multiplied by negative m over c. And we get that our velocity is equal to negative m over c times e to the negative c over m t times g minus c over m times v sub 0 minus g time, actually we have our multiplying in the middle already, and this is our answer right here. So this is our answer with an initial velocity, and let's actually check something real quick. So when you plug in 0 for v sub 0, you get that negative m over c times e to the negative c over m t minus, or multiplied by g minus g. So that just means times this minus 1 times g is equal to our velocity with an initial velocity of 0. And now let's take the limit as t approaches infinity. This just becomes 0. So this gives us negative 1 times negative mg over c. So this just becomes mg over c is equal to our v at t is equal to infinity, or our terminal velocity. And now let's go ahead and do a quick check with our force equation. So we had that our mass times our acceleration was equal to our g minus, or our mg minus cv, and we wanted our net force to be 0 since it would not be accelerating, so its final velocity. So it means 0 is equal to mg minus cv. Now go ahead and add cv to both sides, and we get cv is equal to mg. Now let's divide both sides by c, and we get that our max velocity is equal to mg divided by c. This is meant to be c. And as you can see, that is what we get here as well. So this just helps to prove our answer correct right here. So anyway, I hope you all enjoyed this video, learned a lot, and thank you for watching.